Okay, hello everyone. I'm Shari Al Musul, so your host today. So this is one of our expert talks from the ML school, and today we have a special guest with us. He's Victor. He's a Google developer expert with us, and without any further ado, I will just invite him to the stream, and we'll just start the session. Okay. Hello, can you hear me?
Yes, I can.
Great. Thank you so much for accepting our invitation for the ML Summer School expert talk sessions. Would you please like to introduce yourself?
Yeah, so my name is Victor Sher. I'm a machine learning researcher, and I'm also GDE for AI. It's truly honored to be part of this ML Summer School, and I'm really looking forward to the learnings.
Yeah, awesome. Thank you so much. Okay, let's just start the session. Let me add the slide to the stream. Great, let's start.
Awesome. So yeah, today we're going to look at GenAI processors. It's basically a new revolutionary uh like library that is just for those who are processing huge batch of data, but are looking like for efficient ways for making the pipeline easier. Uh, in the modeling process, right? And it's optimized for TPUs. We're going to look at TPUs. Let me just move forward. Yeah, we're going to look at TPUs, and then we'll look at like the evolution timeline of it's been, the programming models, and then real world applications, then the benefits and access. So unfortunately, I've run out of my credits for Collab. I was hoping I will have them by today, but yeah, they're delayed. So no problem. But I'll show you the code that you can be able to run after this because I think this is like intro to. So code work is basically like building up on the work. So yeah, we'll start off. So chapter one. So you're going to look at TPU, right? So like TPU is basically okay, yeah. So TPU is basically like parallel compute processing, right? We know right now in the era of language model, the era of foundation models, it's it's we are processing graphics, right? We are processing this data graphically, and that way it's a very heavy computationally. So if you use your ordinary CPU, you find it gets harder. So now we have GPU. I know you've heard of GPU, but so for GPU now, yes, GPU specifically goes to the graphical, right? Now that's the AMD, the Intel, and now the common one, NVIDIA GPUs. So GPUs are tightly integrated with Google's TensorFlow software. Yeah, that's for one. The same way GPUs, especially NVIDIA ones, come in with the PyTorch embedded in the kernels, right? Easy for programming the CUDA, right? So here TensorFlow is embedded in, right? It enables seamless execution of machine learning models and providing it significant speed ups for both training and inference. So yeah, it's very easy now for because now this is just the ecosystem. It's all like if you want to build around like Google, uh, all of it just right. TPU is very good at that, right? You use TensorFlow, you're packing it in, maybe Google data sheets, all that. So it's easier, right? So it does all that. So Google's tensor processing units are custom designed AI accelerators, yeah, specifically built as application-specific integrated circuits to handle neural network machine learning tasks. So they're basically ICs, right? So if someone who is done electrical and electronics engineering tell you that they're basically just piles of ICs stacked together, and then we form what you call these processing units, whether it's GPU, whether it's TPU. Anyway, so the specialized features now, the key features include the matrix multiplication. So this is matrix multiply unit. MXU is basically the internal, the corporate, the name for it, but it's the matrix computations, the matrix multiply. As you know, these neural networks are basically uh 2 by 3 or 3 by 3. They are just dense matrix multiplication units, and this is what you have for and for TPU, this is what we have the MXU, right? So high bandwidth memory. Again, there is training and inference requires high bandwidth. Remember, most labs actually, if you go to DeepMind, it's not like they have the data center there. It's far away. It's like a distance, right? Like kilometers. So you like there's a lot of connection, high fiber bandwidth that is connecting, that's linking them together and enabling that. So with GPU, it accesses that and it uses high bandwidth memory. So it's easier for the engineers at the lab just to do it quicker and faster, right? With the iterations. Yeah. And then proprietary interconnect topology for multi-chip scaling. Yeah, this is the part that like the secretive, the trade secrets. Yeah, but you can go look at TPU at in depth. I think I will also share with that for those who are interested to go deeper. Okay, so enough from TPUs now. Now we're going to move forward now to like look at the core functions. So the training large models. Actually, Gemini is trained on TPU. The original, even the second iterations are just trained on TPU. So TPU we would say like accelerating the training of large AI models. And by the way, this is if you go to read the papers, if you sit around with people in ML, they will tell you this is one of the secret why the models for Gemini are good. For example, in large window context because of TPU, there is something about them. Like they're super good. And it's not other labs. They're proprietary, they're internal only. So Google hasn't shared them with like other labs. So such as those used in NLP and computer vision, reducing training time and computational costs. Yeah. So again, like it's like naturally, if I make something on my own, if I use it, that's cheaper for me, right? Instead of sourcing someone else for the same materials, right? Yeah, if even if you're building a house, for example, it's cheaper if you had the materials rather than buying them. Okay, so this is just an example on the computational costs. Then we have the real-time inference. So like there are also improvements for real-time inference that are super quick. Inference is just like when you hit enter at ChatGPT and you're like, how is the day? Then when you hit enter, what comes out, that's inference. That whole process is inference, right? Yeah, so they're optimized for real time, so it's super fast, enabling low latency predictions and high throughput processing. Remember that high bandwidth memory we mentioned? It's part of the like data center operations. The good thing about AI, there are a whole lot of fields there, like data center operations. There are people who are making that, right? That work, that part. So making them ideal for deploying trained models in production environments. Yeah. So that's another benefit. Now, going forward, the evolution, we're going to look like real quick. This is not something I want to focus, but just give you background context. So 2015, internal deployment. Google first deployed TPUs internally in 2015, using them to accelerate various machine learning workloads within the company. That's the first. Then moving fast forward, 2018, Google made TPUs available to third-party users via the cloud. So yeah, okay, a quick distinction. They don't share the actual hardware. They offer you via cloud, right? So if you go to Colab, you'll be offered via cloud. Yeah, so that's a quick distinction. So they don't sell to you like the way Nvidia sells, right? The actual hardware, but these ones they sell to you the APIs basically, yeah, by Google Cloud, right? Allowing external developers and researchers to leverage their powerful capabilities. Now that's 2018. Now Google decided. Now 2018, you'll realize if you go back, if you've been like following Google's when Google Brain was peaking and then Google AI is also peaking, right? At the same time, the previous year, it's when the attention is all you need. Paperhead come out. So now things are on bata building. So there's a lot of uh, there's a lot of works around like large scale models. Okay, then 2024 we have like Trillium. Trillium is like the third iteration. And then, sorry, the sixth generation. I'm sorry, I confused it to another processing. Yeah. Google announced the sixth generation TPU called Trillium 2024, which developed significantly. That's Google I/O. Go and watch Google I/O 2024. This was when the announcement was done. Then IO node introduction. This is like now the seventh generation iteration now of it, designed specifically for the age of inference and parallel compute. Now we are at the age of test time compute, high inference. So this is what IO node comes to do. But yeah, this is just like a bit of context. Now, the performance improvements. Now, each TPU generation has brought substantial performance gain, with the latest node offering 42.5 exaflops. So now, training cycles are measured in flops. So exaflops at the highest, like, right, of training cycles, right, making it more powerful than the world's largest supercomputers. Chapter 3. Now we're going to like look at the architecture deep dive. So now, the TPU at the core vision, when we mentioned there's a matrix multiplication that goes on it, right? That's at the core of it. Actually, that's the core of parallel processing, parallel compute processing. There's a whole matrix multiplication. So utilizing a systolic array design to efficiently perform matrix operations. Now, the high bandwidth memory, the one that you mentioned, we contain connecting data centers to the lab, to the engineers and researchers, is high bandwidth memory provides ultra fast memory access, reducing bottlenecks and data movement, and enabling the TPU to run large data sets. This is a latency issue. You find that when you're processing, even not, don't just go to like the GPU, just look at your CPU. You're just doing something on Kaggle, and then you train a simple data set of like what 1 gigabytes, right? Depending on on your compute power, the CPU, if it's a 4 GB, it could do. If it's a 2, well, tough. But 4 GB, it's a bit struggle, but it could do, right? Yeah, so that's it. That's the same way. So that's the latency, the issue that connecting between processing your data and the output. That's the latency we're talking about. That's the speed, the bottlenecks that's with GPUs it's reducing. And then the XLA compiler magic. Again, I'm brushing off on some things because like we want to like look at the processor, the intro to GenAI processors, right? The library itself. So the XLA compressor compiler. So there is a compiler. There's like your simple compiler in what PyTorch, in your favorite language, or Java, there's a compiler. So, the same way here, there's a compiler. The XLA compiler takes computational graphs from machine learning frameworks and then compiles them into optimized TPU machine code, right? Then next is parallel execution. At the core of these supercomputers now, it's parallel computation. Always remember that. So here they have their own technology. They call it single program. At Google, it's called single program multiple data, SPMD, right? Parallelism. So instead of, again, people in electrical and electronics will tell you this, or telecommunications, like when you're connecting, for example, let's look at bulbs, right? The best way, the optimal way, any electrical engineer will come to do like bulb circuits at your home will do them in parallel. That way, a downtime in one doesn't call downtime in the every other, right? So they will survive. Unlike when you connect them, sorry, in linear form, downtime in one ensures makes the other fall immediately, right? It's the same thing here. So don't worry about like the term itself, just basically how they are doing it, how they have copyrighted it, at Google. Now the memory optimization, XLA optimizes memory layout and pipelining, ensuring that computation communication are overlapped for maximum efficiency, reducing the idle time. Again, the smaller the latency, the more the memory, and then the reduced time for processing, right? Yeah. Now the programming models, now chapter 4. So we have at the core, we have like common one, like the common one used in machine learning. We have four, right? JAX, PyTorch, Julia. Julia is more scientific work, scientific computing, astronomy, weather forecasting. You'll find works around there. And then TensorFlow. Like, these are the four common supported at it, but best. So you can see I've even separated JAX and TensorFlow. These are core Google, right? So they are very optimized for TPUs. Okay. Wait, I'm brushing over because I want to go to the main task of this. I want to like give you a background context at the same time. So the optimization techniques now here. So effective TPU programming involves using large batch sizes, sharding data. Sharding is like optimizing like data in what quantization you want, right? If it's in 32, in 16, just like patterns, like how much small, how much how much adjustment you make to the data, right? So that's sharding. And then model parameters. Parameters are the connections. A model has a billion, sorry, a model has several connections. That's how it flows. That's how communication flows. For communication works, it flows around the neural networks, right? So you'll see they're saying, oh, llama has what, 20 billion parameters. That's the connections in it. That's the settings in it, right? And then employing mixed precision with bfloat 16. Bfloat 16 is again like there's a setting. When you're training, you want to, depending on the compute, you want to either do bfloat 16, bfloat 32. Okay, this is just for optimizing memory usage. So you'll find if you have smaller compute, you just do bfloat 32, but bfloat 16 with the TPU, it's very good. Okay, yeah. So these are just terms like in model training, but don't worry too much about them. You can read upon them slower and slower. All right, so now looking at like the real world application, because now this is the important part. I find that you get a more context about like software or just technology if you get other applications. How is it used in the real world? Okay, yeah. So now, one, language models, large language models. So model training, TPUs are effective for training large language models. Gemini and Palm, all of this, like I mentioned, are using TPUs. Real-time inference. Now, inference is the serving, how it's how the model is being used as to you as a user. That's the endpoint, right? That's the inference. So whether it's just like TTS, text to speech, or there's just like text outputs, like the way with the chat models, the way you do, right? And then vision and scientific workloads, computer vision, event in medical imaging. I know they do that at Isomorphic. Isomorphic is also another lab. They do that on like X-ray data. They use TPUs there to like scan the X-ray images. And then you have scientific computing, so the things around climate simulation. Remember I mentioned climate and weather forecasting, astronomy. That's Julia. Julia is a very, very efficient programming language for that. Okay, and then medical imaging. So in medical imaging, now GPUs help analyze volumes of data quickly. Yeah, again in X-ray data, like I was mentioning. Recommendation engine. Yeah. So for example, YouTube has like a section of it that's just actually, yeah, there's like 85% just like purely TPU, like the whole recommendation system. So enabling, so how YouTube sometimes is so good, like matches all that. These are powering it. It's the TPU. Okay, so now benefits now and access, uh, cost efficiency. So with Gen AI processors now, we get high cost efficiency when you're using them. You're accelerating training and inference at a very much lower cost on your hardware and like your time too, right? So also energy consumption, because having these machines, having these workloads takes huge compute, and with that requires too much power, too much. If the more you train them, like for example, and Gemini was trained in like what, 6 months. So imagine the amount of power it's consuming, right? Yeah, the original Gemini, that is Gemini, the original Gemini that, yeah. So the performance gain. So with TPUs now, if you're using, like I was mentioning, the settings around bfloat 16, you're getting heavy matrix computations very fast and efficiently. So they're all fitted. You know the good thing about these systems, that it's fitted there. So you're not going to do the matrix computations by yourself, but it's just fitted in the system. So for you just to program the kernels, right, how you want them to train along the lines. Okay, now, yes, getting started parts. This is where I was really hopeful for, especially Google Colab. I prepared a whole, what is it, notebook on it. I wanted just like to run, see the examples, but unfortunately, I'm run out of TPUs and I can't. But I'll share with you, okay? And my email is there, open. We'll do it. If you in case you have like, if you in case you have like use case you want to do, please reach out. Okay, yeah. There's one is Google Colab. So Google Colab offers free access for experimentation and research, allowing users to try out TPU capabilities without any cost. That's one. Then the Google Cloud Platform. If you have a color, if you have, if you have, both, if you have the card, like right, so if you have the credit card in there, you get like 30 days, right? 30 days free for to rent TPUs. That's 30 days free. Then after that, you can either rely on credits, maybe from Google like extended events, like Google developer events mostly, or just buy them. If you're at an organization, if you're just doing personal research, you can just buy them if you get grants. And then there's the TPU Research Cloud. It's a program. It's basically a program that grants like credits to so separately. So you have to prove you're conducting large scale research without worrying about costs. Okay. Yeah, so that's it. So yeah, I was hoping here I would have gone to the code, but yeah, no, anyway, that's it. It's just like simple code with like the three different. I had them in three different examples: Jackson GPU, then a training a simple model on GPU with TensorFlow, and then now a large model training pattern. That's for us to see the how GenAI processors work. But yeah, that's it. So unless you have any questions, yeah, that's it. Thank you so much for attending
Okay,
the session.
Victor. So as you mentioned, you have the code, right?
Yeah.
Maybe uh, can you share the link right now? Maybe it's in maybe the Google Colab link or GitHub link or something. Have you uploaded that
Yes,
anywhere?
yes, yes. Let me see. Let me see.
Okay.
Oh, no, 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 no. I haven't uploaded it yet, but I can upload. I
Hmm.
thought I had uploaded it on Collab anyway. I haven't done yet, but I can, and maybe I can share with you via email. Is that okay?
Yeah, we can do that for sure.
Yeah.
Then I will just add it to the description or the chat section. No issues.
Th- Thank you so much.
Okay, great, great. So, okay, I believe, okay, we can just wrap up the session right now. We don't have any questions yet, but if we have any questions in future, because it will be there in the YouTube, obviously, then folks can reach out, obviously, and I will share your mail there as well. So, yeah, great. So, yeah, I believe. Thank you so much, Victor, for your time.
Yes, thank you so, Thomas, so much for hosting me. This was a really great session. Uh, I was really honored to be here, and thank you so much. So just anyway, oh yeah, yeah, sorry. So yeah, just I was quickly following up, but I will share with you the documents so that we can move from there because that was also a core part of this. We can talk about like how we're going to use it all, in case of any troubles, which lessons, anything. uh, you can share with them my contacts and then we can proceed with it. But thank you so much for attending. It is my
Okay. Thank you, sir. Okay. Bye then.
own. Thanks.
Okay.
Bye.
Okay, great. So, this live, it was shorter live, but the thing is, we're supposed to run a code, but our speaker was had lack of credits for now. So, the code will be shared with you via the YouTube comment section or the description section. So that's not going to be an issue. So you can just do that. You can just run the code and you will understand the process as it has been already mentioned throughout the slide. So thank you so much and hope to see you in the next week.